Hello, my name is Vladimir Mankov, and on behalf of Vladimir Deart and Irina Krasnova, I present you report on the article entitled Evaluation of the Effects of Processing Data on Network Traffic Classifier based on machine learning methods for quality of service predication in real time. The main idea that inspired us for this topic is the development of dynamic real-time quality of service approach based on machine learning methods and new capabilities for collecting statistics in the SDN environment. Despite the source of our inspiration, the result of the analysis of the mechanism discussed in our work can be applied to any networks and not only to SDN networks. By the time we move to the machine learning classification block, we assume that our model has collected general real-time statistics on the flow and individual statistics on packets. This imposes certain features on the nature of statistical data, which we will use when constructing the feature matrix. The methods and new features of collecting real-time statistics using P4 language in SDN environment are described in more details in our previous works. To show the next purpose of our work, we place on this slide the third block, traffic engineering, which will be based on classification results. This is not the focus of our current work, but this goal leaves its mark on the nature of our research. Our traffic classification model consists of 5 stages. At the first stage, there is a collection and systematization of statistical information about network flows. The flow is a sequence of packets with the same 5-tuple cortege: IP source, IP destination, protocol, port source and destination. The second stage is the construction of a matrix of features, which consists of the sizes of each of the first 15 packets of the flow and the arrival time between successive packets, as well as characteristics calculated on their basis. The third stage, data preprocessing, is a key element of this work. Since the data is collected on a real network, the feature matrix has outliers and is represented by features built at different scales. Many machine learning methods are susceptible to statistical anomalies and depend on the presentation of the data. Our hypothesis is that based on data preprocessing methods, we will be able to improve the classification results. This block will be presented in more detail on other slides. After constructing the feature matrix, the data is divided into train and test sequences. On the train sequence, at the fourth stage, the model is trained, and at the fifth stage, the trained model is tested on the test sequence. The accuracy score was chosen as criterion for evaluating the classification result. Early work showed the effectiveness of scaling and normalization for classifying traffic for intrusion detection purpose. In our work, traffic classification is carried out in order to assign quality of service classes to flows. So we have expanded the set of presented methods to 9, which can be used together or separately. In particular, the first step is to work with outliers. Outlier removal, out, replaces outliers with the median value. Outliers are samples that exceed the standard deviation. As an alternate, it could be used an approach based in consideration about outliers on 3 standard deviations. Then one of the transformation and scaling methods is applied. First of all, scaling standard corrects the data to standard so that the mean is 0 and the standard deviation is 1. Scaling min-max scales the data so that it ranges from 0 to 1. Scaling robust, the data is the range between 25th and 75th quantile. Centering is relative to the median value. Power transformation, mapping data to a normal distribution using power transformations. Power transformations are a family of parametric transformations that map data to a distribution that is as similar as possible to Gaussian distribution. Quantile transformation, a nonlinear transformation based on mapping the cumulative distribution function to the uniform distribution and then to the Gaussian distribution. With this method, the most frequent values are propagated to reduce the effect of outliers. Since the transformation is nonlinear, it may distort linear corrections between variables measured at the same scale, but renders variables measured at different scales more directly comparable. Normalizer. Each sample is normalized independently to a norm equal to 1 in our case. The poly method can be used to generate additional features based on second-degree polynomials. On the next slide, you can see scaling examples. The figure base shows 4 features for 100 samples. The data is randomly generated and represents a normal distribution with various parameters. You can see how the distribution pattern changes when the min-max, robust, or standard methods are applied. Here it is, power and quantile transformation for the same data. In the last figure, 2 additional features have been added using the poly method. Let's have a look on machine learning methods, which score grow was analyzed. First of all, decision tree, a logical model consisting of nodes, leaves, and branches. Each node contains a certain conditional function based on one of the features. This function splits data in different directions, which ultimately comes to one of the leaves associated with certain classes. A random forest represents a number of such decision trees that are built and make decisions independently of each other, and the final classification result is determined by the voting of most trees. XGBoost, the most hopeful method for our case, consists of set of decision trees, but unlike random forest, they don't work in parallel, but sequentially, one after another, correcting the errors of previous classifiers. Gaussian naive Bayes is a probabilistic model based on Bayes' theorem. In the case of Gaussian naive Bayes, the distribution of features is considered normal. Logistic regression is a linear classification method using a logistic curve describing the possible probabilities for a specific flow. K-nearest neighbors assign specific coordinates to each sample object depending on its feature vector. For the predicted class, k-neighbors are selected to distance to which is minimal. The resulting class is determined by the most common class among k-neighbors. And the last method analyzed in this work, neural network, multi-layer perceptron. It's implemented with input, output, and multiple intermediate hidden layers. This input layer consists of a set of neurons based on flow features. Each neuron of subsequent hidden layers uses weighted linear feature summation with a nonlinear activation function. The classification result is obtained on the output layer. We took decision tree and method based on them for testing, since in most works of traffic classification, it was the random forest method that showed the best results. The rest of the methods were chosen so that they were based on completely different working algorithms. The experiment dataset was captured on a real network by the MAWI research team as part of the WIDE project in January-February 2020. From this data, we selected 1,500 streams from 13 most common applications for TCP dataset. 250 streams from 8 applications were used to analyze the UDP dataset. As can be seen from the results of the experiment, replacing the outliers with the median values increased the classification results for all methods. For a TCP dataset, up to 22% in case of MLP. And for UDP datasets, more than 19% in case Gaussian naive Bayes. Determining the outlier by the out method as a value lagging from the median by value no more than standard deviation shows better results compared to the out value 3 STD, in which the outlier is considered to be a value lagging from the median by more than 3 STD. Therefore, for further analysis, the out 3 STD method is not considered, and the out method is used in conjunction with various methods of scaling, standardization, and normalization, increasing the classification results. Random forest, decision tree, and XGB methods as algorithm based on the construction of random tree are least susceptible to outliers and data sparsity. Therefore, the use of data preprocessing methods compared to other methods slightly improved the classification results. Nevertheless, replacing outliers with the median value allow increasing the classification results up to 5.89% for a TCP dataset and up to 6.5% for a UDP dataset. The accuracy of the Gaussian naive Bayes method was increased by 37% for a TCP dataset while using quantile transformation and removing outliers, and by 45% for UDP datasets with the help of preprocessing based on min-max or standard scaling methods and removing outliers. For logistic regression, the accuracy is improved by 52.9% using a quantile transformation for a TCP dataset and 49.75% using a power transformation for a UDP dataset. In the case of K nearest neighbors method, the quantile transformation increases the classification accuracy by almost 13% and thus reaches 80% in case of TCP dataset. Normalizer increases the accuracy by 8.25% for a UDP dataset. As a result, the K nearest neighbor method becomes a competitive classifier with an accuracy of more than 94%. Unlike other machine learning algorithms, K nearest neighbors accuracy decreases when using some scaling methods. For example, in case of UDP dataset. For the MLP neural network, the accuracy increases by 49% in cases with the TCP dataset, and for UDP up to 68%. Thus, 68% is the largest increase in accuracy obtained using data preprocessing methods, allowing the accuracy to change from 19.25% to 87.75%. In general, the best preprocessing methods for the collected TCP and UDP dataset are power and quantile transformations together with outlier removal. As can be seen from the presented results, adding not linear dependencies for the results together with removing outliers not only doesn't improve the classification accuracy, but even worsens it. For algorithm based on a decision tree, random forest decision tree and XGBoost, the accuracy also decreases regardless of what additional preprocessing methods are used. This is due to the features of the mathematical model construction. However, for other algorithms using power and quantile transformations, additional not linear dependencies increases the classification accuracy. Thus, the accuracy of neural network classification increases up to 3%. K nearest neighbors up to 7%, and in the case of logistic regression, up to 13%. For naive Bayes, accuracy is almost unchanged. In further work, it is planned to add to the model the ability to detect and classify the new flows that are not presented in the training set. Also, we're planning add traffic engineering based on the results of classification and study the performance of the whole model.